All right, we're live.
We're live already. So welcome everybody. We have with us, this is the first and last, Professor Kaelbling with us, Leslie. And we're pretty excited. Let's see. I'm gonna have a little introduction if you want to share the slides. Do you have the slides?
All right, I have to figure out how to see that.
Cool. All right. So very briefly, so she's a professor of computer science and engineering at MIT. She received a degree in philosophy, which is very interesting, and a PhD in computer science, both from Stanford University. She's done research primarily on reinforcement learning and robotics. Now, I actually looked at a little bit the career, and there's way too many acronyms, but I think that's a really good thing when you're a professor, right? So, but there are three that I want to highlight. So the founder of JMLR, which is a journal of machine learning research, and the story behind that is actually pretty interesting. So I recommend you go to the wiki page or Wikipedia and read a little bit about the motives of that. She's a member of the CSAIL, Computer Science and Artificial Intelligence Laboratory, and a fellow of the AAAI, so Association for the Advancement of Artificial Intelligence. Now, a couple of fun facts. So she was actually at Brown University until 1999. And why do I bring this up? Well, because Professor Littman obtained his PhD from Brown University in 1996. So yes, Professor Kaelbling was Professor Littman's doctoral advisor, which is a fun fact, in my opinion, anyway. So in 1995, she co-authored a paper titled Reinforcement Learning, a survey with Professor Littman and Professor Moore. The paper has over 6,000 citations, according to Google Scholar, which is a lot. And it's I would say even now, it's still a really good introduction. If you want to actually, have a good introduction, that covers a lot of the topics in a digestible, I'd say, 80 pages probably. So she has been cited over 20,000 times. And according to nameslook.com, the name Kaelbling means pioneer, inventiveness. How suiting, right?
Are you serious? I have never heard that before.
Yeah, fun facts.
Okay.
And finally, Professor Kaelbling is well known for her research, but also for her outstanding balancing skills. And if you don't believe me, you have to go to her personal or her professor website, which shows you a proof for that. So no, but in all seriousness, thank you so much for being with us. It's a pleasure for us, the TAs, the teaching staff, and the students to have you. And yeah, let's, if you have anything to say, we go there and then start reading off the questions.
Okay, cool. Well, I don't know. This is kind of fun. I have never actually live cast to an audience that I can't see, but I can see the TA people here on my screen. So I feel like if I do something really horrible, I'll see it on their faces. But I teach almost, like I was just saying, last semester, I had 650 students in introductory machine learning at MIT. So it was kind of like a MOOC, but actually just not remote. It was massive. So anyway, I am happy to answer pretty much any question you want to ask me.
Excellent. Val, you're going to be helping with the questions?
Sure.
Awesome.
Give me just a second because I had a technical difficulty already.
Oh, no, so quick.
I can vamp. Yeah, Michael was my first PhD student.
Isn't that incredible? I actually didn't know about that, and then I started, researching to do a little intro, and
yeah,
that is so great.
Yeah.
Can you guys see the?
I actually don't work on reinforcement learning anymore, but we'll get into that, I'm sure.
Yeah, I saw that. I guess robotics is the big thing, but there are many related things, I suppose.
There are.
Yeah. Excellent. So, all right, go off.
Cool. So the first question is, when state and/or action space is too large, how does one make exploration more efficient? At early learning stages, it is possible to break the high dimensional space into lower dimensional space and find an optimal policy individually before exploring the full space. Sorry, is it possible?
Yeah, I got that. So that's good. So that's a good question. in fact, I think that's like the critical question to be asking, right? So it's pretty clear that reinforcement learning stuff works nicely when the state and action spaces are small or they're continuous, but they're smooth, or you can average or interpolate in a nice way. But as they get more and more complicated, then yeah, the standard reinforcement learning methods don't work so well. So a lot of people are trying to make some kind of hierarchical reinforcement learning. And if you understand in advance how to design the hierarchy, like if you say, oh, I have a robot and first I'm going to train it to move and to pick things up, train it to do individual things, and then I can say, okay, now I'm going to try to train a policy at some high level of abstraction that then uses those basic abilities as if they were actions. So that's a kind of thing that people are working on. And more recently, there are methods where a human doesn't have to say what the subparts are. You don't have to say what these high-level actions are supposed to be. The system is supposed to kind of figure that out for itself. And those methods, without any help at this point, they don't necessarily work super well, but with even a little bit of signal about how to break down a problem, then it's often possible to learn a kind of a reasonable hierarchical strategy.
Great. That makes sense. I guess we'll go on to the next question now. So many of the advanced techniques for machine learning, reinforcement learning, and AI in general tend to be quite resource intensive. When working in resource-constrained environments like embedded systems and robotics, does that restrict the kind of algorithms and approaches that are used, or are many adaptable to such an environment?
Right. Okay. You guys ask good questions. That's a good question too. So I used to work on reinforcement learning, but after my thesis and roughly that survey paper, I quit. At least I quit working on reinforcement learning in the most typical way. And this is in large part why. So I think the key is absolutely figuring out how to generalize from not too many examples. And there's a whole bunch of subfields of machine learning that get at that. People talk about transfer learning, for instance, where you can learn from many related tasks so that when you're given a new task, you can learn much more efficiently. It's also usually true, and there's a lot of really interesting research on this, and your Professor Littman has done some of it, which is that there are, I don't know if you've studied yet, the idea of model-based versus model-free reinforcement learning methods. Is that something that you guys have covered? Yes? Okay, good. Yep. Yeah. So generally speaking, models are awesome because, at least I think, because they're very reusable. So when you learn a policy or a value function, typically it has the reward kind of baked into it, and you've learned a policy that does this thing, and that's really good if you're flying an airplane or bicycling or juggling, and it's the task is pretty clear. It's like you should build it in. But if you're trying to learn, I'm interested in really general purpose AI. I want to make lieutenant commander data, right? I want to make like just a general purpose intelligent robot. And so I want it to be able to solve any problem that presents itself. And it's very hard as you kind of address more and more complicated domains. It's hard to anticipate what the problems would be in advance. And so if you learn a model, so something that lets you predict the effects of your actions, and you learn it in a kind of a form that's compositional, right? So that you can reuse pieces and parts of it to solve different problems. Then you have a toolkit to solve all kinds of problems that you wouldn't have even anticipated when you were learning. So at least in my view, model-based methods and then model-based methods with interesting structure are likely to make it so that we can learn from fewer examples than kind of the basic techniques that one starts with. Oh, what's my vision for the future of reinforcement?
Well, before that, I actually have a follow-up on that because I think it's very interesting what you mentioned there, you know, model-based, model-free. And one of the things that I'm very interested in is like, sometimes you for example, even, you know, let's talk about like Monte Carlo estimate versus TD estimates, right? Yeah. The extremes have some particular advantages. This is really good at this. but it has more variance. So this is very, very good at this other thing. If you do model-based versus model-free, you also have the two extremes. If you do policy-based versus, like policy-based, for example, or like doing policy gradient methods are a little bit better for like robotics versus doing value-based because of the continuous actions, right? And this kind of things. And it seems to me that, to actually be able to build a general purpose system, we're going to have to find a way to integrate all of these things so that the agent does some kind of meta learning to know what to use in a particular circumstance, right?
Yeah, no, I agree with that completely. So for instance, on my robot, I don't have a problem with using policy learning for the kind of primitive actions, right? If, we're right now trying to get the robot to do some like pouring and stirring and stuff like that. And I think that's like a really good place for tight loop policy learning. I learned how to stir or pour. But then what we do as soon as we learn a new primitive is we try to learn like a formalization of the preconditions and effects of that primitive at a higher level of abstraction. So I might say, if I'm learning to pour, I might want to say, oh, okay, I learned this really nice pouring skill. It works pretty well. But I still need to know under what conditions it will work. Because the robot doesn't live to pour, right? It's trying to make you a drink or do whatever. And so you have to say, well, okay, for the pouring to work out, as a function of like the thing I'm trying to pour into and the thing I'm trying to pour out of, what should their relationship be in height, and what should the velocity be that I use in my pouring controller, and it might depend on whether it's honey or water. So I need to learn a set of conditions under which that thing will work. And then if I learn that, I can put it in my high level kind of more cognitive or whatever planner that can say, okay, I'm trying to make a drink. I need to pick this up, put it here, pick up this other thing, do some pouring and so on. So you're absolutely right that like there's no good reason to fight. People kind of get into these little religious wars sometimes about this method versus that. And you're absolutely right that like they almost, maybe some are just like useless. I don't know. But most of these ideas are good in some way and they probably have a place. And it is a hard job to figure out what the place is and when to use what kind of method.
Yeah, thank you.
Great. So yes, if maybe this is also a repeat from the last question, but what is your vision for the future of RL?
Yeah. So, yeah, I really like this question. I don't think we should be thinking about if you take RL to be a technique, we shouldn't be thinking about the future of a technique. We should be thinking about families of problems and what problems we're trying to work on and what the best way is to address those problems. So I think, a better question might be, what are problems that we want to solve that we can't solve right now? And then since this is a class on reinforcement learning, you might ask, let's say, that involve some agent that interacts with a world that needs to get better over time, right? So then the answer is, well, that we might treat that at that outer level. It might be, you could see it as a reinforcement learning problem, but internally you might treat it in an interestingly mixed kind of way. Like you could say, my problem of trying to teach my robot how to do complicated things, in a certain sense, that's a reinforcement learning problem, but it's not a reinforcement learning problem in the sense that we're just going to like pull out some algorithm for the textbook and apply it to the whole thing. So here's the problem that I worry about most right now is a kind of a methodological problem, right? Which is, we know from the theory of machine learning, maybe in the past you guys somewhere have studied the bias variance trade-off, or the idea that if you don't have enough data and you have a complicated model, you might overfit. So we know that even though it might seem like machine learning gives you something for nothing, it doesn't. And that the answer has to be contained in the combination of what you build in and what the data brings. And if you don't build anything in, then you need a really big pile of data if your problem is complicated. And so back to the how do we learn from not too many examples, stuff does have to be built in. So for me, the kind of interesting question is, well, what? So I like to say that my job as a robot engineer is to do for my robots what evolution did for me. So humans and other animals are born with like not just generic goo in their head, but actually a fair amount of reflexes and internal computational structures and all kinds of stuff. Like there's a lot there already. And so, and whatever is there is an awesome scaffold for learning. It puts us in a good position to learn. Maybe it says, oh yeah, you need bits that are like policy search, and you need bits that are like high level strips planning models, and you need different pieces that do different jobs. Maybe that's what's in there. I don't really know. But my burning question is that, like, what should I try to build in and what should I try to?
That's a very nice answer. I just want to say one thing is like, it's very interesting and you know, the more, because, you know, I guess I've been, you know, reading more and more because I've been TAing this course for a little while, but the more I read about reinforcement learning is the more I sort of learn about myself as well, which is really interesting, the connection, right? Because it's like, how could you be learning, you know, you go like, oh, sure, off policy, on policy. I kind of get what this is and how this actually works internally. So what you said about basically, you know, doing for your robots what evolution did for you is a very interesting comment. Very nice.
All right. So this one's a little more in the weeds. Can you describe a small set of best practices that you recommend to someone that wants to solve problems with reinforcement learning techniques? That is, how to go about the problem, what to look out for, and ways to avoid trouble.
That's interesting. No, I'm a terrible person to ask this because, as I said, I don't really actually, I don't do too much reinforcement learning. I mean, I think, so one best practice, okay, but this is something that students of mine, so my PhD students generally do stuff that is not necessarily what I'm doing. So I have many of them who do reinforcement learning. I mean, so one important thing is to be sure that you first try to solve a problem that you already know the answer to. So it's so tempting to say, oh, okay, I'm going to use reinforcement learning to solve this big, but this applies to pretty much any machine learning thing, right? That your first attempt should not be on the problem that you care about, right? And you should have some nice sequence of problems, the easy one and the one that's so easy that you think it would be impossible to get it wrong. So that's the one you should start with. And then you should have the easy one and then the medium one. And so that, because it's really hard to debug, as you probably know, right? Most students first, before they start doing machine learning, they're used to writing computer programs, and they know when it's wrong because like it draws the wrong picture on the screen or it raises an error or something. When you do machine learning, you write a program and numbers come out and you're like, oh, cool, numbers, like it didn't crash. But you don't know whether those are good numbers or bad numbers. It's very hard to tell. And even if it's machine learning and you run it and it says, I got 75% correct, and you don't know yet whether that's a good idea or bad idea. So
it's like, that's why we have random walks and carpools.
Right. You have to start with really easy stuff. And the other thing is, like, it's almost always pays off to spend time building visualizations or ways of trying to see what the heck is going on in there so that you can tell why because it won't work. Like the first N times it won't work. And so it's so easy to say, oh, I'm just going to mess with it until it works. And messing with it till it works doesn't, I mean, sometimes that can eventually work out, but usually you have to figure out what's going wrong. And then that requires like patience and deep breath and backing up and saying, okay, this is not working. How can I creatively set it up in a way so that I can tell what's wrong? So I don't know, I think a lot about debugging.
Yeah, I feel like it's good life advice in general.
Yeah.
All right, so this is a long one. When teaching a robot using reinforcement learning methods, I assume you usually do a lot of world truth simulations before the first time you actually use the real robot, and then apply your simulated model in the real hardware and continue learning from there. What do you do if the robot is supposed to operate in an environment that is too difficult to simulate in a computerized physics engine, or if the robot itself is too difficult to simulate, for example, a flexible snake-like robot in a marine environment, or a firefighter robot, etc.?
Yeah, that's a good question. So I think you're right that I mean, we do everything in simulation as much as we can first, just because usually if it doesn't work in the simulation, there's no chance that it will work on the robot, because the noise models are all weird and stuff on the real robot, and it's slow. I think there is nice work. One of my students just did some work in this area, but several people are thinking about an idea of it's called meta-learning now. It kind of used to be called transfer learning, but the idea is that in simulation even, you might create several possible different simulation worlds. Like they might have different gravity or different friction or different kinds of ways of moving or something, and they might not be so reliable. But what you could try to do is learn some basic pieces. So you might learn some primitive pieces that can be composed to solve your problem. Or you might learn some basic skills that have a parameter, like a gain parameter, but not 100,000 parameters in a giant neural network. So in the simulator, you might be able to learn something like a template for solving your task. And then if you have something like a template for solving your task that doesn't have too many free parameters anymore, because again, it's like, as you probably know, the size of your hypothesis space is related to how much data you need. And so you might be able to figure out the rough shape of a solution and then put it in the robot and just get enough data to tune it up or to figure out which versions of the modules you need to solve the problem. But that's fundamental, yeah.
All right, so the next question is, what are your thoughts on some of the research coming out of companies such as Google, DeepMind, OpenAI, etc.? And how do you see the relationship between business and academia evolving in the field of RL?
So that's interesting. I mean, so listing OpenAI as a company is not quite right, I think.
I guess they're a non-profit company. Does that
right.
count?
Like I used to work at SRI, which is also a kind of a not-for-profit. It's kind of like a company and kind of not quite. But I think OpenAI is even less of a company than SRI is.
Oh, because it's only research, right.
Yeah, and I think it's more like a foundation, but I don't really know. I mean, I think it's a pretty interesting ecosystem, as they say. I worry in general that both the companies and academia right at the moment, there's such a frenzy, there's so much enthusiasm and there's a bunch of stuff there's a lot of, as they also say, low-hanging fruit. There's a lot of things you can do pretty quick without a ton of work, and it's kind of neat. And so lots of people, I'm not answering your question, I'm answering a related question. I can come back to this question. But so companies necessarily, I mean, for-profit companies, generally speaking, have to have a short horizon because in the end, they're beholden to somebody to make some money. Academia has the luxury, in principle, of having a longer horizon, like a research horizon. But unfortunately, we're in a little bit of an arms race. So the companies are like, they have a ton of money, they're spending it, they're hiring professors and students with great salaries. And they have, I think, a really exciting working environment. So they're doing really good work. But it is changing what happens in the universities, partly because many of the faculty are not so present, and partly because the cycle time is quicker. And the quick cycle time is good for some kinds of innovations, but I think it's bad for other kinds. And so I worry that a little bit that the competition and the pressure from the companies is making academia less likely to play its role of having a longer horizon. And that's bad, because some people have to like sit in their offices and think for 2 years before and do something different and difficult and weird. And if we lose that, then we lose an important kind of, I think, component of the research portfolio of the field in general.
I actually have a follow-up.
Yeah.
So I'm really interested in knowing your opinion. Like, so sometimes you hear about, the hype that AI creates as something negative, because, I guess at one point there was a hype, and then, the AI winter and whatnot, and people like don't want to put more money because the expectations grow with the hype, and all of a sudden we don't deliver, and chaos, right?
Mhm.
But to some extent, I believe. Well, I personally think that some of the hype is actually good because students get more interested on it. You attract more people to actually pay attention to it. Of course, it's not to have the hype is not good if you want to do research, right? While you're doing research, you cannot be just like jumping. You just have to be focused and have a more scientific mind. But what is your opinion about the effects of that, hype around AI and what it creates really, I guess, in a more general level?
Yeah. Well, no, I mean, I think you're right that it is good and bad. It is good because there are more resources, right? So there's like more funding, and there's and there's an enthusiasm, and that's good, right? Enthusiasm is good, but it's also and the core of what's going on right now, I think, is very exciting and very important, and there's something real in the core. But then there's also like just this giant cloud of people who don't really know what they're doing, who talk and talk and talk and say how cool it is, and you're going to get something for nothing, and please buy my snake oil. And so that's bad. That's bad. So it's hard to say. It's partly good and partly bad. But the thing is, it is affecting academia. So you say, oh, the academics have to stay and think their deep scientific thoughts. But the problem also is that no, but they also have to play in that same market with everybody else. And so I can't say to my students, don't work on that short-term thing that's almost surely going to make a paper that will get published somewhere. Don't do that. Just do something else that's longer term. Just wait for 2 years and don't read archive and come out and do a thing. I would like to say that actually, but I think it would be professionally bad for them. So I personally do completely contrarian research. I have always done stuff that nobody was doing, and people found it hard to appreciate. They often find it easy to appreciate later, and that's okay. But it's hard to advise students to do that. I have the luxury of doing it because I'm like old and tenured.
Actually, I have a student right now making a comment. And research versus hype sounds like the exploration versus exploitation problem.
Awesome.
This is a comment.
Yeah, that's about right. That's good.
All right. Since an RL agent learns by trial and error from the environment and gets rewards, how can RL agents work seamlessly, flawlessly in dynamic environments such as self-driving cars where there are lots of moving pieces?
Well, so I think maybe the question is, what is the state, right? So in reinforcement learning, we spend a lot of time thinking about how to formalize the world in terms of something a process that has state and actions that change it over time. So it is true, especially if you come from an engineering background. I finally learned this, but people from engineering, when they say the state of the robot or the state of the car, usually what they mean is the position, like the position orientation. And so you're right to say, well, gosh, if I have to worry about somehow the self-driving cars is more complicated than that, and it is true. But I think then what you just have to do is in some way expand your notion of what constitutes a state. Now, that's a hard modeling problem. So here's the other thing that they might not tell you in the class that you're taking. I don't know. See, I get to tell you things like some wicked auntie or something. You can learn all the algorithms, and that's pretty fun and pretty clear, and you can take exams and you can remember the formula for the Bellman equation or something. But the hardest part always is not that, but modeling. The hardest part is taking the tools that you have about reinforcement learning and walking up to a problem and saying, how can I see this as a problem that the tools in my toolkit will apply to? So if you want to say, oh, I want to see self-driving cars as a reinforcement learning problem, you have to say, what's my state space? And you might say, oh, it's my position and velocity. well, that won't do. Maybe it's my position on velocity and what lane I'm in and how many people are in front of or in behind me and whether it's daylight and whether there's a stork flying over to the left of me and what's on the radio. Okay, so then it could get really long, and if you make it too complicated, that's too complicated. So what's like the minimally complicated notion of state that would let you treat this problem as a reinforcement learning problem? You might have learned that you should have the Markov property, but you can never really have it. So that's hard. That's hard. It's much harder to think about how to apply these tools to a problem than it is to learn about the tools.
So what do you see as being the biggest challenge to AI and reinforcement learning research over the next 5 to 10 years? Some examples are addressing questions regarding AI and ethics, increasing the number of industry experts, or embedding a large autonomous system like driverless vehicles in society.
I do not know the answer to that. I am, like, for good or ill, a very myopically research-oriented person, which means that as much as possible, I put my head down and try to solve the technical problem before me. So I refuse to answer questions about what's going to happen in the future, what technology is going to work, how many years from now. I just won't even get into that because I don't know how to predict it, and everybody who tries is usually wrong. Yeah, good, thank you. I just don't want to do that question. I love it.
So this question is a little involved. They had a project where they were trying to land a lunar lander. And so this was our first adventure with function approximation. So when we tried to implement reinforcement learning in Project 2, both I and my classmates found that the probability to land the lunar lander on the pad successfully is not 100%, no matter what kind of deep learning algorithm we implemented. We also know that even a small probability of failure may incur catastrophe, which we can't afford in the real life. Just like we may not be able to afford a failure landing of a real lunar lander in real life, even with a probability of 1%. How can we improve the outcome of deep learning so that we can apply it in our industry like robotics, aerospace, etc.?
Yeah, okay, so that's good. That is really interesting. Right, so because it's so easy to say, wow, I got 99%, that's really good. But you're exactly right that there's all kinds of cases where 99% isn't good. And especially if you're, imagine, okay, so at least if you're doing the lunar lander, it doesn't have to land too many times. If you're doing something having to do with making decisions in an autonomous vehicle, it makes decisions, several times a second. And that's a lot of decisions in a month or a year. And they all have to be at least not too terrible. There's some interesting work that people are starting to do that actually allows a kind of verification of deep networks that use ReLU units. So the interesting thing about ReLUs, right, is that they're linear or zero. And that means that you can think of the system as being some kind of a crazy combination of a whole bunch of linear systems that kind of switch in and out depending on the inputs. But at any given moment, given the inputs, the thing that you have is linear. And the one thing that people know how to kind of analyze is linear systems. And so the fact that ReLUs are kind of at core linear means that some tools and techniques that exist in verification and validation of engineered systems can start to be applied to trained up neural networks. So I think that's actually a really interesting direction. Now, in reinforcement learning, it's super extra much harder because the validation problem. So if your validation problem is just it's got something to do with, I don't know, I don't make mistakes of a certain kind in one step, that's not so hard. For lunar lander, to analyze whether the lunar lander is going to work, you have to think about how its behavior is going to unspool over time, right? And you'd have to really do what a control engineer would do, which is to make a model of the plant, right? Take your model of how the world works, take the policy or whatever that you learned, put them together and try to do some analysis of that whole system. So it's very important and hard.
I think there are other fields that are related to sort of like artificial intelligence. I guess the researchers in artificial intelligence usually use environments from other, like, you know, pre-established environments or computer like games and things like that. But I think there are other fields, I think operations research maybe, or, you know, the control theory. There's some other areas that are similar to reinforcement learning that study a little bit more in depth the actual environments. Is that
right?
Correct?
That's right. I mean, I think anyone who thinks about going forward in reinforcement learning and applications in the world should definitely study control theory, because although they study relatively simple systems, they can make very strong proofs about the system, and they understand. It's a good vocabulary. I think it's a good mindset for thinking about how does the whole system that I get when I combine my learned thing with the world, how does that whole thing behave? Because that's what you have to prove something about.
All right, so I think this one is related to the question before it in some ways. What are your thoughts on ethics in automation? For example, what responsibility does a self-driving car manufacturer have if presented with an ethical dilemma, such as choosing between saving the life of a driver or a pedestrian? Since humans rarely agree 100% on the right course of action to take when presented with certain decisions, how could the right course of action be decided in robotics?
Right, that's also a good question. It's interesting how captivated we are by this question, because it's okay, it captivates us because it's kind of an interesting moral question and you can talk about it at a cocktail party and so on. I mean, the worst problems of automated vehicles are not going to be it trying to decide whether to run over the granny or the toddler. It's going to be like bad perception and slipping on ice and stuff like that. Okay, but so I think that we, right at this moment anyway, are spending too much time thinking about this, but I think we are thinking about it maybe because it's a proxy for some longer term concerns about robots taking over or something. So I think, okay, so I'll tell you a small story because I think it's useful to tell, and it relates to this, and then I'll answer the question. So not too long ago, some people from the military came to talk to me, and because they were very smart, well-educated ethicists from the military, and they were working on a report about autonomous weapons, and so they wanted to talk to me about autonomous weapons and some technical aspects and some ethics and so on. And the first thing they asked me was, has your robot ever done something you didn't expect? Straight face. And I was like, well, my goodness, the question you should ask is, does it like ever do anything I expect, right? And what I realized is that after talking to them, like, why did you ask me this question? I can't even understand it. That their view of the way that we would program a robot is like, well, it would be like the way you program your Lego Mindstorm or something, that it's like, well, do this and then do this and do this, and then if this is true, go left, otherwise go right. Like it's a very, very imperative sequential kind of thing. And you could imagine that if I wrote a program like that for my robot, it would be surprising if the robot did something I didn't expect. Okay, but nobody programs anything in AI like that anymore. Right? The way we program a machine learning system, a planning system, an optimizer, all these things, is that we specify a space of possible solutions. We specify some kind of objective function, right? It should fit the data well, it should get a lot of reward. And then we do some kind of automated search algorithm to try to find a good answer in the space. And so for us, once we've got the algorithms done, right? So once you have a good search algorithm, a good reinforcement learning algorithm, then the programming problem is actually back to kind of what I said before, is setting up the space and the objective function. And of course, now what happens is when that's your when programming is no more programming the algorithm, but defining the space and the objective, then the programmer really is quite removed from the behavior of the system. Right? So I say, oh, optimize reward. The joke is like, well, if I ask my robot to get me a cup of coffee, I don't mean at all costs, right? It should not like run over people on the way to get me coffee. So then the ethical, or that I think the interesting both technical and ethical question in some sense is, how do we think about programming as the problem of specifying utility functions or reward functions? And if you've done reinforcement learning to try to solve a problem, you may have had the experience that you write down a reward function, your reinforcement learning algorithm works great, it optimizes that reward function, and you end up with behavior and you're like, oh no, that is not what I want. I mean, I remember one time the first time I tried to get an actual real little robot to do some reinforcement learning thing, and it was moving around more than I wanted to. I wanted it to turn in some circumstances. I can't remember. So I changed the reward function a little bit, and then I told it shouldn't touch things. And so then it would just spin in place. Because it was like, well, okay, you told me not to touch anything, so I'm not moving. I'll just spin. Thank you. Yeah. So, okay. So now there's this question of like, well, what should our utility function be when we ask the robot to do something? How do we say, yes, robot, please get me coffee, but don't do this, but don't do that. Don't hurt people. Don't hurt, yourself. And there's interesting work going on right now at Berkeley. So Stuart Russell, who was actually a colleague of mine in graduate school, and somebody named Dylan Hadfield-Winnell, who was one of my undergraduates at MIT, who's now a graduate student there, they're working on some interesting game theoretic stuff having to do with the problem of making a robot that's really very capable, but that would allow you to turn it off. Right? So imagine that you're in a debugging cycle. Here you are, debugging, but now you're not debugging your learning algorithm anymore. You're debugging your utility function. You're debugging the reward function. So you say, I think this might be a good reward function. And you type it in, and you put it in your robot. The robot starts to act, and you watch it, and you think, oh, no, that's not what I wanted. And so you want to say, okay, robot, stop. I'm going to put in a new reward function. But like if the robot is really good and really smart and really capable, and you've told it to do something, if stop is not consistent with the thing that you just told it to do, it won't let you turn it off. Right? So then how do you combine, as an engineering problem now, as a game theory problem, how do you make a robot that's very capable at doing stuff, but that was still guaranteed to let you turn it off so that you could bring it back and change its reward function? So you should go read about that stuff.
That's a very interesting one. A related question is that, so why, I guess you have a philosophy also background. Why you think humans are okay with a 99.9% performance of a human, but not of a machine? Like if a machine is 99.9, we don't accept that. But, well, it's a human, he can make mistakes. Why is it?
Well, I think we will accept it. I mean, I think, let's see, humans are pretty bad drivers. And they're bad at a bunch of other things. And I think once we can document that the automated systems can do better than the humans, people will eventually accept it.
People will be fine with it.
Yeah.
Looking forward to it.
Yeah, I mean, a simple example of this is in some kind of, at this point now, medical image, like read, I'm not going to get this citation right. It might be looking at pap smears, or it might be some other medical kind of image test reading problem. So this is one where I think that humans are pretty good. Like a really good human who's totally focused and on task can do it really pretty well. But humans get hired to do it for like 8 hours a day, and nobody could do that job for 8 hours a day. And so then they start to slip and not do very well. But you can, I think at this point now, for many problems like that you can train up a computer to do it. And that computer is not going to be perfect. But you can just do the numbers and see that the accuracy of the computer is probably going to be better than the accuracy of the people. And I think that will be accepted right away. Because that doesn't feel so terrifying, right? You're kind of removed from it. But then I think things like that will just creep in, and we'll get more and more used to the idea, and it'll be okay. And think about the autopilot when next time you fly.
Great. We've been studying deep reinforcement learning algorithms such as deep Q networks. Do generally intelligent robots that you have worked on make use of such algorithms, and if so, how?
Yeah, so mostly no. what we're doing right now, though, I mean, so just the kind of the story of the system that we're working on right now, we basically hand built kind of a hierarchical perception and planning system for our robot, so that we could understand what we think is a good architecture. So the architecture is things like, well, there's some low-level loops that run quickly and some higher-level process that reasons and some estimation thing that tries to aggregate the input from the object detector over time. So we've kind of made some architectural commitments to the system, and what we're doing now is actually trying to take away some of the stuff we've built in, trying to figure out what seems like the essential parts of that architecture and what parts we should be able to learn from data. But nowhere has DQN come up. So, I mean, one thing about Q learning is it makes a strong Markov assumption, right? It assumes that you have access to a state which really tells you everything you need to know instantaneously about what's going on in the world. That is really often, hardly ever, except in games, the case. It also assumes that, in a certain sense, I'd like to ask students who are really enthusiastic about DeepQ to think about traveling to Tibet or something. So making a complicated journey. You can solve a lot of different problems that might come up in that process. Flights get canceled, things get flooded, people have a heart attack on the airplane. I mean, I don't know, all kinds of stuff can happen. And to think about that as a problem that you would solve using DeepQ, even if you could think of what the state would be, is to have figured out the solution to all possible things that could happen. All of them. And I just don't think that's realistic, right? So I think that, again, for a class of problems. So as I think that as the class of problems, as the problem space gets bigger, and as the part of it that you're likely to personally ever encounter becomes a tiny sub-manifold in this giant space of things that could happen, it doesn't make sense to me to try to pre-compile your reaction to all possible situations, which is what DeepQ tries to do.
And this is also related to the Markov assumption, I think, is what you're saying, that because you have to build the state space that is like such that there's no history, right, involved, or there's no need for history. Sorry.
Right. So the combination of the Markov assumption and then the fact that the state space is just like unthinkably big. Like, it's not just the state space is big; it's like the number of dimensions of the space is unthinkable. Right. How many dimensional is the space of traveling? You know, I don't know.
Right. I guess so. Okay, I guess the question will be then, because DQN is probably, it's not even, to be used in robotics, starting with you have no continuous action. So if the student would have asked something like, for example, the Berkeley guys are working
on PDPG, which is kind of like DQN.
Right. And how about like GPS? I guess there's some. Yeah, GPS.
Yeah, right. So there's a whole bunch of continuous action methods. No, continuous states and actions is not, I think, the big problem. I think it has to do with, as you say, the Markov assumption, and with the actual size and variability of the states that could come up, and whether you can address them all in advance.
Great. So this is pretty high level and there's a lot of text, so forgive me. This is a very exciting time to be working on AI. Unlike back in the 80s when AI seemed to take off to later fade away for some time, it looks like recent advances in computing power have made possible what wasn't before. We are able to get tangible results from the application from applying machine learning algorithms today, and that has undoubtedly excited the entire industry. However, it seems that there are still some missing technical pieces to get from where we are to real and complete AI. Do you think we are any closer to the next breakthrough that will keep the momentum going? Where do you think these next advances will keep pushing this field forward will come from?
Okay, so, well, the unlike, so I'm not so sure that the unlike is unlike, right? So, okay, so back in the 80s, people were super excited and some stuff was working that didn't work before. So, I mean, things are always cyclical, right? So we're all super excited right now. I think we have definitely made advances. I think, you know, again, that the enthusiasm is maybe a little too much. So, but of course, we need a million more insights. I mean, I think, so there's a lot more pieces to figure out between here and general purpose intelligence. And I think, you know, as I said, I'm interested in trying to understand some things. I have been talking a little bit more to people in cognitive science and brain science, not because I feel that I am necessarily constrained to try to solve problems in the way that nature does, but if I can learn something like, for instance, what gets built into natural systems, that gives me ideas about what I can build into, I might be able to build into systems, or if we learn that certain kinds of reasoning mechanisms seem to be present, then that's interesting. So I think of course, we're closer than we were before. I think we need a lot more breakthroughs. Where will they come from? Well, so I think they'll come from some people who keep trying the hardest problem instead of the easiest one. I think we have to be sure that some people keep doing that. I've known, you know, and lots of people, and it's impossible to predict who will figure something out. But you won't figure out something important if you're not trying the hardest problem. I think that that's true.
I think we may have skipped one, and perhaps for good reason. But you studied philosophy in undergrad. Is that related to cognitive science at all, or it was just?
Not really. And, you know, it is true that I have my undergraduate degree is in philosophy, but it was at Stanford. So if you haven't studied philosophy, then you won't know that there's all different kinds of schools of thought in philosophy and so on. And there's a part of philosophy that is almost math. So it's kind of logic and thinking about like what is knowledge, and like I used to worry about what is representation. If you want to say something inside my computer represents something in the outside world, what does that even mean? How can you talk about that? Could it be wrong? So anyway, so the kind of philosophy I did was like almost math and AI already. So I wasn't really worrying about the meaning of life. And I didn't really think that much about morals and ethics and that kind of stuff either. I mean, that's a part of philosophy. There's a bunch of parts of philosophy. So I was really focused on something that's almost AI. So it wasn't like I had a giant change of heart or something. Also, the fact is that when I was at Stanford, there was no undergraduate degree in computer science. So that's probably what I would have done. But it's not related to cognitive science much at all. Cognitive science is about the study of actual humans and what kind of behavior do they do. And cognitive science can give us insight into, for instance, the kinds of problems that humans find easy and hard. So one important thing is when you solve AI, when you think of yourself as an AI person and you, for instance, find that some problem that you're trying to solve is formally undecidable or NP hard or otherwise difficult, if you're like theoretical computer science, once you prove the problem is undecidable or NP hard, then you say, okay, that one's done, let me find another problem, because now you know you can't do that. On the other hand, AI people don't do that because they say, oh yeah, it is true that formally it seems like all the problems we're trying to solve are like computationally hopeless, but yet we have existence proofs in humans that they can do some version of the problem. And so studying like, and sometimes I think we as AI people are crippled by trying to make AI systems too good, right? So you might say, oh, my robot has to be perfect. It has to go all the way, always straight down the hallway, or never take a stupid action. But if you watch people doing something, they don't go straight and they take a lot of stupid actions. And so that gives you a certain like, you can relax a little bit and say, okay, I don't define the optimal solution necessarily. And you can get a sense of like what might be reasonable corners to cut. I'm really interested in what corners I could try to cut. So, yeah.
If you were free to,
wait one second. One follow-up on the previous question, which is like the unlike back in the 80s when AI seemed to take off and later fade away for some time. I wanted to ask you, you think it's different the way that we have it today, given the investments come from companies that are profitable, and those are really the ones that are making the, not the only I guess not the only sources of income, but back then, I don't think only probably IBM was investing a little bit on, in the deep blue. No. Okay.
All the car companies, the oil companies, every big company was doing it.
But were they profitable from AI? Because Google, for example, and
No, I see. No, I think, no, you're right. So it's working much better now. Much better.
Because my hope is that that changes things a little bit, because we have the Google Assistant. You can say turn the light on, and that's pretty good, and then it's making money for them. So I guess they are more likely to continue the investment regardless, right?
That's right. No. I think that's right, and I think that it's like you reach a new high water mark, right? So what we're doing right now is figuring out this kind of current set of techniques and ideas. Where will it take us? And it'll take us a certain distance, and it'll take us farther than we are now. But it's also just, I don't think that, I think it's also guaranteed that it's somewhat overinflated, just because.
Yeah. Well, it's human nature, I guess.
Right. No, it is. It absolutely is. And it's probably part of having a good cycle, right? Is to get some overinflation. So I don't really know how to predict the degree to which.
This iteration is going to take us.
So some bubble is going to pop, but what's the size of the thing that remains when the bubble pops, right? It might be almost as big as the bubble, or it might be some little teeny nub. I don't really know.
Right. Yeah. I guess we have time for one more question, and I think it's a very good one.
If I could research anything I want. Oh, sorry, I'm reading. Yeah.
No, that's fine. Yeah. No restrictions, infinite funds, and no regulations.
Well, so I'm happy to say that regulations don't stand in the way of the research that I want to do. So that's not a problem. I'm not really tempted by anything illegal. And, I'm in a really lucky position in the sense that I can do I'm doing pretty much what I want to. It would be, the only thing that keeps me from really focusing on research in the way that I would want to focus on it is that there are too many other things to do that also seem worthy, like talking to you guys, right? So I spend time teaching classes and doing other stuff because it seems like an important part of my overall job. So if there's anything that's holding me back, it's like the fact that there's too many worthy things to do. But really, the research topic and the way I'm trying to address it is like, it's pretty much what I want to do.
That's awesome. But I think we are about to wrap it up. I guess I went to the next question, but yeah, we have a bunch more questions, I can assure you. And actually, we have follow-ups too, but thank you so much. We are very passionate about AI and machine learning and all the hot words, whatever. But also, seeing having firsthand your time and your comments and all that is really exciting. So thank you so much for putting the time. We really appreciate it.
Okay, it is good to talk to you all.
Bye. Stop the broadcast.